Hi, this is Mrs. Basin. Today we're going to talk about enthalpy of reactions, which is section 5.4. So when we're talking about enthalpy of a reaction, this is the amount of heat or the enthalpy change that accompanies any kind of chemical reaction. To get the overall heat of reaction or enthalpy of reaction, you take the H of the products minus the delta H of the reactants. A couple other things to remember. Enthalpy is an extensive property. So what that means is how much enthalpy is associated with a reaction depends on how much of the reactant is consumed during that reaction. The sign of delta H, the sign of the enthalpy, depends on the direction of the reaction, so whether or not it's absorbing energy or releasing energy. And then finally, the enthalpy change depends on the state. So when you're looking these values up especially, you have to pay attention to whether it's a solid, a liquid, or a gas. So when a process is endothermic, delta H is positive. So that means there's energy being put into the system. If a process is exothermic, then delta H is negative, which means heat is being released or energy is being released from the system. So just in summary here, a couple key points. Enthalpy is an extensive property, so that means it depends on how much is there. Delta H for a reaction in the forward direction is equal in size but opposite in sign to delta H for the reverse reaction. So if you think back to those Hess's law problems we did, if you reverse a reaction, you reverse the sign, but the number is the same. And then finally, delta H depends on the state of the reactants and the state of the products. Okay, so this is how this particular aspect of enthalpy is applied. So if we have a reaction, and you can see the reaction here is methane gas burning, so this is the methane bubble reaction that we've done in class. When you have 4.5 grams of methane, how much heat is released? So I know I have 4.5 grams, and this ties into that idea that enthalpy is an extensive property. So this value that's given is for however many moles of CH4 are written out in that particular equation. So according to the equation written here, there's negative 890 kilojoules of heat released per 1 mole of CH4. So if we have 4.5 grams of CH4, that's a different amount. So we're going to have to do a conversion to get to how much energy would be released per 4.5 grams. So I'm going to start with my 4.5 grams of CH4, and I'm going to convert that to moles. So 1 mole of CH4 is equal to 16 grams of CH4, and that's just the molar mass of CH4. And then I know from up here, there are 890 kilojoules of energy released per 1 mole, because that's the coefficient in front of my CH4 in my problem. So I go through and do this, and I end up with negative 250 kilojoules. So that means for every 4.5 grams that is burned, I release 250 kilojoules of heat. Okay, so one more example. Hydrogen peroxide can be decomposed into water and oxygen by the reaction given below. And again, tie this back to class. This is the elephant toothpaste reaction. So we have liquid hydrogen peroxide, and it decomposes into water and oxygen. For this particular equation, the way it's written, that releases negative 196, or releases 196 kilojoules of energy. And again, by looking at this, we know it's releasing energy because it has that negative sign. So that means the energy is being given off, or this is an exothermic reaction. Now, the way this particular problem is written, this value is per 2 moles of H2O2. So if you wanted this value per 1 mole, you would have to divide this in half. Okay, so now what we're doing is we're calculating the value of Q, and again, we said for now, we're going to say Q equals delta H, so those two things can be used interchangeably, when 5 grams of H2O2 decomposes. Okay, and again, this up here, this is per 2 moles, but we have 5 grams, so we're going to do a conversion to figure out our value. So we have 5 grams of H2O2. We're going to convert it to moles because this is 196 per 2 moles, so we need to get rid of the grams and go to moles first. So 1 mole is 34.02 grams, again, just the molar mass. And then I know this is releasing 196 kilojoules per 2 moles of H2O2. And the reason we have a 2 there is because of that coefficient right there. Usually these are written per 1 mole, but this particular problem was per 2 moles, so you have to be careful and watch out for those. So then we'll go through and calculate that. That would release 14.4 kilojoules of heat. Again, it's releasing. We know it's releasing because that value is negative, so this would be an exothermic reaction also.